Hi, welcome back. Here in this video, we're going to be looking at some examples in reference to electric potential difference. The first example here that we're going to look at is simply just relating electric potential difference to charge, to potential energy, or to the change in potential energy. Imagining that some charge is flowing through some circuit, let's say, and in doing so, its energy is changing as it's maybe moving. A battery is pumping up a charge's energy. We're going to look at how electric potential difference is related to that energy. So, in our first one, we're saying that maybe it's a battery, a 1 volt difference between the negative terminal of a battery and the positive terminal of a battery. And we're going to move 1 coulomb of charge. Remember, in our first video, we said 1 coulomb is an extraordinarily large amount of charge, but for simplicity's sake, we're just going to say that that's what it is. But we're going to move 1 coulomb of charge through this electric potential difference. We're going to move it from the negative terminal to the positive terminal, where it will gain 1 joule per coulomb of charge. So remember, that's what volts means. It's joules per coulomb. So let's see what that looks like. So potential difference, right? Potential being V, difference being delta, is the change in the electric potential energy of a charge divided by the amount of charge. Rearranging that so that we can actually figure out the change in electric potential energy of this charge, it's going to be the potential difference times the charge. And so here we had a potential difference of 1 volt. We had a charge of 1 coulomb. Let's rewrite this potential difference in the units that make a little more sense. Instead of volts, it's joules per coulomb times charge. And we can see our units work out pretty nicely here. We have charge on top and we have charge on the bottom. They cancel out and we're left with joules, which is energy. So we have 1 joule of potential energy. By moving 1 coulomb of charge through an electric potential difference of 1 volt, it gains 1 joule of potential energy. There's a change in potential energy of 1 joule. Example B, we're saying that to move a certain amount of charge, sorry, let me fill in the table up here. For example B, we're going to move a certain amount of charge. We don't know how much charge through 3 volts, and that amount of charge gained 12 joules of potential energy. How much charge would gain 12 joules potential energy if we moved it through 3 volts? Okay, so again, change in potential or potential difference is the change in electric potential energy per charge. Rearranging that to solve for charge is the change in electric potential energy divided by the potential difference. 12 joules is how much potential energy this charge gained. It moved through 3 volts. We get 4 coulombs of charge. The unit analysis there is a little trickier. If you want to work it out, change volts to joules per coulomb and you can see that it will work out. But this is saying that 4 coulombs of charge will gain 12 joules of potential energy when it moves through 3 volts. Because think about this, 3 volts is 3 joules per coulomb. And if we have 4 coulombs, each of those gaining 3 joules, we will have a change of potential energy of 12 joules. Perfect. Okay, this last one's the easiest because we don't really have to rearrange anything. The electric potential difference when 6 coulombs of charge gains 30 joules. The potential difference when we have a change of electric potential energy per charge of 30 joules for 6 coulombs. This tells us that we're going to have 5 joules for each coulomb, which is 5 volts of potential difference. Okay, and our second example that we're going to look at is something called an electric potential diagram. This is something that's going to help us visualize what's going on with the energy at different parts in the circuits. Where do certain parts of the circuit have the same amount of energy? Where are these voltage drops? And what do those look like? And how do charges actually flow through a circuit? So let's look at a very simple circuit to start with. This one here on the top left, a 1.5 volt battery, means this battery has the capability to give each coulomb of charge 1.5 joules of energy, and we're hooking it up to a light bulb. This is a very, very, very simple circuit, the most simple circuit you can build. And so here on our potential diagram, we can see here at the bottom we have a place where we can show the locations on this circuit that have 0 volts, 0 joules per coulomb of charge, and the locations that have 1.5 volts, 1.5 joules per coulomb, and potentially there could be locations that are in the middle of that, maybe has 1 volt of charge, or maybe has 0.5 volts of charge, or sorry, of potential. So let's start here at the positive terminal of the battery. At the positive terminal of the battery, this location has the highest potential. This is location A, up here at the top. Another location that has 1.5 volts of potential is location B. A wire is typically assumed to take no amount of energy for a charge to move through it. This is called an ideal wire. So to move through a wire, a charge doesn't have to expend any energy at all. To move through a circuit element like a light bulb or a resistor or anything else that is being powered by the circuit will take some energy, but just to move through a wire will take no energy. So to move from location A to location B, we'll draw a little arrow, show that this is the direction that a positive charge will flow. If it starts at location A, it will flow to location B and keep the same amount of potential, keep the same amount of energy. But then these charges are going to flow through this light bulb. And they're going to flow through the light bulb and they're going to end up, well, you can see here locations C and D are also connected by a wire, which means that those two locations are going to also have the same amount of potential. And if location D is at the negative terminal of the battery, we would say that that has a potential of 0 volts. That's location D, which means that location C must also be at 0 volts. And so to go from location B at the top of this light bulb to location C, all of the energy that these charges gained by going through this battery are going to be dropped. There's a voltage dropped through this light bulb. And then the charges are going to travel back to the battery. And then once they get to the battery, well, the battery is going to re-energize them and give them 1.5 volts, 1.5 joules per coulomb of energy. So here's a very simple electric potential diagram. What we see here, as the charges flow from A to B, they maintain their potential. Here, we're going to have, this is like thinking about our analogy, this is like the water slide, right? This is our water slide. This is a voltage drop. Whereas over here, from D to A, this is like our water pump. This was pumping up our water. This is the battery that is doing work to lift, quote unquote, these charges from the low potential location to the high potential location, from the negative terminal of the battery to the positive terminal of the battery. And here, up at the top and at the bottom, we can see that these circuit elements that are connected by a wire, are at the same potential. Okay, so that will always be true. Any circuit elements that are connected by wires directly are always going to be at the same potential. Okay, let's look at our next example. This is a slightly more complicated circuit because we have two light bulbs now connected to each other. They're connected in a certain way. We call this setup a series circuit as opposed to a parallel circuit. Our next example will be a parallel circuit. We'll look at, more in detail at series and parallel circuits in a future section, but we'll look at this simple series circuit where we have two light bulbs connected together. There's only a single path for the charges to flow, so that's going to make things a little bit easier here. So first, let's start at the location that has the highest potential, and that's here at the top of the battery. And connected directly to that terminal by a wire is location B. So location A and location B have the same potential. So charges will flow from A to B and they will maintain their potential, maintain their energy. Then we're going to drop. We're going to go down a water slide. But we're not going to drop all the way down. We're not going to get all the way to the negative terminal of the battery. By the time we drop through this first light bulb, we need to have some energy left to go down the next drop. So we're going to drop some amount. Not sure how big these light bulbs are. If they are identical light bulbs, then we would actually drop halfway, 3 volts. Half of the energy would be used in one light bulb, half would be used in the other light bulb. But we're not certain, so we're not going to label exactly how much energy is dropped, but it's enough to say that some of the energy is lost, but not all of it. Okay, so that's location C there, where we have lost some of the energy, but not all of it. And then to go from C to D, well, C and D are connected directly by a wire. There's no energy lost when we move through a wire. So here's location D, and then to go from D to E, we're going to drop, and we're going to end up all the way at the bottom. This is you crashing down into the pool at the very bottom of the water slide, and you're going to have to walk all the way back up, or the water's going to have to be pumped all the way back up to the top to go again. So this is location E, and then the charges are going to flow. It takes no energy for them to flow to location F, which is at the bottom terminal, the negative terminal of the battery, and then the battery is going to charge those all the way back up to 6 volts so that they can flow again through this circuit. Okay, and our last example here, this is what's referred to as a parallel circuit, where we have elements that are connected, both ends of elements are connected to each other. And so it's a little more complicated here because charges have different paths that they could take. They could flow through one light bulb or the other light bulb, but they don't have to flow through both, whereas they did in the previous example. So let's set this up with location A being, again, at 6 volts. This is a 6 volt battery. Location A is 6 volts, and location B connected directly by a wire. So it takes no energy to go from A to B, but also notice that location C is also connected directly by a wire to B. So again, the same amount of potential at location C. A, B, and C all have the same potential. A charge that flows from the positive terminal of the battery will have the same amount of energy at location A, location B, and location C. And then notice that location D, E, and F are also all connected directly by wires. So that means that location D, which is the opposite of location C, so this is location D, location E, and location F, are all connected to the negative terminal of the battery. They're all going to have 0 volts of potential. And so we can see, so let's think about a charge flowing from location A to location B, then dropping through the light bulb, and then flowing back to the negative terminal of the battery. So from A to B, dropping all the way to 0 volts to location E, going back to the battery, and then the battery is going to charge it back up, and it's going to be able to flow through there again, or the charge could flow to location C through the light bulb and then back to the battery. So it could go from A to B to C, drop down to D, and then flow back to the battery. Right, so notice that charges could take multiple paths in this scenario, but no matter which path they take, they will use all of their energy before they make their way back to the battery. Okay, that's it for electric potential difference. Stay tuned for our next topic.